I thought I would go back to my practice of uploading both technical videos as well as those with more general appeal. And this is one of the technical ones. Covariant differentiation. As a student, I am presently studying General Relativity in an attempt to someday be able to reconcile it with quantum physics and create a theory of quantum gravity. And presently, I am in the phase of more deeply studying the general relativity part of it. Last summer and spring and summer, I was studying quantum field theory and electromagnetism, more the classical electrodynamics, and then the quantum electrodynamics. And then I received some inspiration to study space-time algebra, which seems to be a very effective vehicle, or an effective tool for unifying quantum physics with general relativity. And now it is general relativity. And so in my review of the topic, the latest thing that I've been looking at is covariant differentiation. And, in the past, I have had some reasonable notion of what it is, but I'm getting closer to being able to wrap my mind around what is covariant differentiation. And it is entirely necessary to know it in order to be able to do general relativity. And it is a very important concept in quantum field theory also. It appears under the name of gauge theory. And in quantum field theory, a gauge symmetry is something where through mathematical modification, you can bring it into the context where everyone should agree on what a certain quantity, a certain electromagnetic quantity is. Well, here it is in terms of relativity. So imagine yourself in a spaceship in deep space, and you look out your window and you see absolutely nothing. Are you moving? You might be. Maybe you're at rest. Who knows? The principle of relativity, and Galileo tells us that there is no way to know if you're moving or not. Now, you look out the window again, and guess what? There is another spaceship, and it's going by. It seems to be going from the front of your spaceship to the back. Are you moving? Still, you don't know. Maybe you are. Maybe you are moving past that other spaceship. Maybe it is moving past you. You go over to the other spaceship, and it's the same question for that observer as it is for you. Now, you can just arbitrarily make the decision with your free will that you are at rest. You are not moving. And that the other spaceship is moving past you, and that is a valid thing to say. The one in the other spaceship says that, makes the decision that they are at rest and not moving, and that you are the one you are the one that's moving from, well, in the opposite direction to what you think they are moving, okay? Also, an entirely valid point of view. Now, if you in your spaceship want to share the same point of view as the other person, you need to perform a Lorentz transformation, a mathematical transformation using a matrix that will allow you to make observations from your friend's point of view in the other spaceship. Now so it's a comparison of motion between the two points of view. Both are valid points of view, and by making these transformations, the two of you can come to some sort of an agreement. In flat space, right, deep space without any gravitational field around, with neither of your two spaceships firing the engines and accelerating, well, that's flat space. And it's a reasonably simple mathematical transformation to carry out to see the other person's point of view. Now, suppose that one of you is in orbit of a planet, or perhaps a black hole, or perhaps one or both of you have fired your engines and you are accelerating. Well, now there is a sense of curvature, and that makes the calculations much more complicated. Basically, we use rulers to make our measurements. Well, a clock is a type of ruler for the dimension of time. We have our spatial rulers, and probably it's going to be some sort of scientific instrument that is much more sophisticated, but it's probably at its heart a ruler. Now, if there is curvature in your space-time because there's a planet, star, or black hole in the vicinity, or because you are firing your spaceship engines and you are in acceleration, right? If there's curvature, just a regular ruler won't work. It'll give you an answer, but it will likely be wrong if you are trying to compare with somebody else's point of view. And basically, when you make these comparisons, you are using a derivative, mathematical operation called a derivative. A derivative is a mathematical thing that compares one quantity's change with respect to another quantity. It's basically a comparison of two things. An ordinary derivative compares one thing to another. That's it. It's accurate in flat space, but if you have curvature involved, it's not good enough. A partial derivative compares one thing with one thing amongst several other things. That increases the complexity, but partial derivatives is an entire subject in itself, and for today, I'm not going there. So what needs to be done is that you have to know how the presence of that gravity from that planet, black hole, star, or acceleration is affecting the measurements for each point of view that you're looking at. And that is where the covariant derivative comes in. Now, the ruler you're using is called a metric, a space-time metric. And there is a complicated mathematical object called a Christoffel symbol that is symbolized by a capital Greek letter gamma. And there are a number of inputs to the symbol that quantify the gravitational fields in your friend's point of view, and it creates a correction factor. So you can use your derivative measure in your own reference frame and it'll work. If you want to understand the measurements that your friend is making, then you have to use the correction factor, the Christoffel symbol. And in terms of a covariant derivative, you are subtracting. So your derivative minus the Christoffel symbol will give you your friend's derivative. So the covariant derivative is basically the accurate way to convert from somebody else's point of view to your own point of view. And to be able to see things like black holes, stars, planets, acceleration through someone else's point of view. Believe it or not, this was a simplistic explanation. I think I need to be able to make it even more simplified to have it understood. And we'll get there someday with these videos that I'm creating. So I will plan to upload this video, and while I'm doing that, I will create my more general video right now.